in the process of transferring heat between bodies or between systems, there are three ways that this can be done. The first method is what we call conduction. Conduction is transfer between neighboring molecules in a substance due to what we call a temperature gradient. Now, conduction is going to occur between solids. So we have solid materials that actually touch each other. Okay, they are in actual contact, and so they can conduct the energy. Examples of this: pancakes on the griddle. So you have the pancake mix. You have a flat griddle. The flat griddle is hot, and so it's going to transfer some of that energy to the pancake mix, and in the process is going to cook the pancakes. We flip them over. Convection. Convection happens between a liquid or a gas. Okay, so of course, in the case of a fluid, there will be physical contact, but again, this is not between solids. This is a fluid. Okay, so it's going to happen either by a fluid or a gas. And if you've never blanched broccoli, it's really good. And I want to bring up this example because there's actually two processes going on here that are convection related. So in the first step, you go ahead and boil the broccoli. So it is of course in contact with boiling water. It's hot water. It's just boiling water. You place the broccoli in there for a few minutes, raw. Of course, it's cooking it, but you just leave it for a few minutes. You don't boil it all the way. Okay, you just want to get that dark green. You want to keep that dark green look to it still. And what you do immediately after that is you take them out and you go ahead and blanch them. And in order to blanch, what you have is you have an ice bath. So you have a bowl full of water and there's a lot of ice in it, and you also put kosher salt to help with the process to keep it nice and cold. And what happens is you're shocking the broccoli molecules. Okay? And so instead of it becoming soggy, it actually it's cooked, but it gives it a nice texture and it keeps it dark green. So if you don't like eating raw broccoli, but you also don't like that gray broccoli, may I suggest blanching broccoli? It's really delicious. Okay, and in this case again, you have convection, right? Boiling with the water was taking the heat from the boiling water and giving it to the broccoli. And then when I threw that broccoli into the ice bath, I took the heat from the broccoli and gave it to the ice bath itself. Okay, and in both cases, that exchange of energy happened because of a fluid. Radiation is due to electromagnetic waves. So if you ever made a solar oven, like a pizza box with aluminum foil and stuff like that, that is an example of radiation. Of course, if you go ahead and do beef jerky and you leave it out, okay, the sun cooks it, that's also radiation because of electromagnetic waves. But the classic example, of course, is the microwave, right? So if I microwave a Hot Pocket or whatever you put in the microwave.
Is there anything today that I ate that wasn't microwaved? The salad.
So here we have a cup of coffee. It's in the microwave right now. You'll notice that there are some molecules in it. They're moving, but they're not really moving much, right? It's room temperature. So we're going to go ahead and push the start button on our microwave. This green line, this green wave represents the microwave itself, emitting energy. Notice that what that microwave is doing to the velocity of the molecules. Notice what it's doing to the kinetic energy of the molecules. So I know we have Fahrenheit for the temperature in America, but the majority of the world uses Celsius, which was a scale that was developed in 1741, and it was based around water, so the idea of water. The freezing point of pure water is 0 degrees Celsius, while the boiling point is going to be 100 degrees Celsius. However, as we got further along in scientific innovation, there was a need for a greater temperature scale, an all-encompassing temperature scale, where there weren't any negatives, but there was an absolute zero. And so we have the Kelvin scale. And the Kelvin scale is defined to have an absolute zero. It's at zero itself, 0 degrees Kelvin. On this scale, the freezing point of water is 273.15 Kelvin, and the boiling point of water is about 373.15 Kelvin. It's very important that you go ahead and find out how to convert Celsius to Kelvin, because that's going to be necessary with a lot of the problems that we do. A cup of water at 40 degrees Celsius and a cup of water at 5 degrees Celsius are left on the table. Now, to give you some perspective here, this would be hot and this would be cold. So unless you're from Canada or from Mexico or from somewhere else where they actually use Celsius, you might be confused. Room temperature, like right now in your room, is probably 23 degrees Celsius. It's between 22 and 25 degrees Celsius. So just to give you an idea, room temperature is going to be about 20-ish degrees Celsius. So keep that in mind as you look at some of these problems. Okay. So let's look at a picture of this. So here's my 40 degrees Celsius. Here's my 5 degrees Celsius. I want to make 20 degrees Celsius be room temperature just to simplify stuff. I do want you to notice that from 40 to 20 is about 20 degrees Celsius, and from 20 to 5 would be about 15 degrees Celsius. If there is a greater temperature difference in between the two temperatures, then it's going to go ahead and change itself a lot faster. So you'll notice that in the first case, right, we have about a 20 degree Celsius temperature difference compared to the 15 down here. That's why you're going to see a greater change, a faster change. So you notice how it's just going to drop a lot faster, versus the one that's coming to room temperature is actually just going gradually. So just to give you an idea of what this means, right? So we have the red and the blue. This is the hot one, right? This is the hot cup, and this is cooling. And this is the cold cup, and it is warming. And they're both trying to get to the same room temperature. Now you'll notice that it takes a while, as time goes by, this takes a while for it to happen. Eventually it'll happen, but it's going to be a lot longer than you think. Okay? It gets close, and it keeps getting closer and closer and closer, but it's going to take quite a while to get to that point. Give non-food examples for each type of heat transfer.